Proper.
Yes.
Yes, ma'am. So like I told Professor Lowell before you joined that I will be in transit.
Yes.
Um so like I told so I'm just trying to make sure I set as much security for the meeting before I move.
Okay.
Yes, ma'am.
Okay. Thank you, dear. So we keep everybody muted like you've done, and all videos off like you've done. Okay. And then just those of us with mics will keep the mics. Thank you
Yeah.
so much. But for
So
those we should handle the admission into the room, right?
yes, ma'am, but that might be a lot.
I'm already on that, ma'am.
Okay. All right.
Okay.
Yeah.
All right. So I think
Okay.
another thing, Professor Labo, I didn't think you can add devices from the group. They can most likely make an announcement, so people rename their devices. That way, it's easier and less stressful for
Okay.
you.
Okay.
But the
Yeah,
YouTube is
I
live,
think it's
and
going to be
so that's fine.
All right.
going to be a lot of work.
Yes, I'll be glad to work with you once I finish the
Okay,
announcement
ma'am.
for the few minutes.
Okay, all right.
It's a lot of
Okay.
work here. Okay. Okay. Good morning, everyone. Thanks for being at this first meeting of the qualitative research. It's actually a big group. We have actually two groups: WhatsApp group, WhatsApp platform for registered members, and each platform has 1,024 persons. So we do know this is a large group. We're going to need help from every one of you to manage this group. One, please do help us to keep your eyes on your devices so that you do not unmute accidentally and you also do not put on your video accidentally. We need you not to put on your videos because of the bandwidth and the possible problem with bandwidth. So please do not put on your video. We have with us today my brother and friend, and I must tell you, I completely think him agreeing to be here is a major, major big deal. He loves research. He loves teaching this. You would hear it from his voice. You will hear it from the way he handles. If you don't stop Dr. Taiwo, he's going to go on for 5 hours. He has a master's in public health from the University of Lagos, but also a master of science in clinical research from the University of Liverpool, and holds a PhD in public health with a specialization in epidemiology from Walden University in the US. Most importantly, he is the Director General of the ICO Center, Intercountry Center for Oral Health for Africa. That's a big position. So having the Director General spend 4 weeks with us is a major, major thing, and I do not take it for granted. If you do not know what ICO is one of the WHO centers in Africa. And I think they're just 6, one in South Africa, one in East Africa. He would correct me. But so having him here for 4 weeks doing this training is a big deal for me. So please celebrate having him here with me. And every time I sit under his teaching, everywhere, anywhere in the world where he is, and I'm listening, I gain something new, despite even what I think I know. Please join me in celebrating Dr. Taiwo as I invite him to take the podium this week. Please note before he speaks that if you have questions, put them in the chat box. We would likely, because of the crowd, not be able to allow you to raise your hands. Put them in the chat box. We are harvesting throughout the meeting. In addition, remember we gave you notes to read, and it's so that this can be interactive. Start to push your questions now. We would harvest it and make it available. On that note, I'd like to invite, I call him Professor Taiwo all the time. I don't think he has anything less a qualification to be a Professor Taiwo. So do welcome me, Professor Taiwo, with my prof in asterisks to the platform. Over to you, Doc. Yeah.
Yeah, it's my pleasure to be on the platform. I really appreciate the opportunity you've granted me to share some of these thoughts as you've always availed me this opportunity. I thank you so much for all the encomiums. And I'm sure we're all going to have a very swell time, have a good time together talking about quantitative data analysis in the next 4 weeks. Just to add to part of what Prof had said, I would like to advise, that as much as possible, we'll try to be available for the sessions, and not only be available, try to be on time also. The way it works is that everything is like built on itself, like precept upon precept, line upon line. If you miss part of some of the deliberations and discussions, it might cause a kind of gap in all we're trying to do. And to the best of my ability, I will try and bring this concept down to the BRS minimum, to the level we can all, appreciate, all flow with. I know we are all from different disciplines, different fields. Research transcends every discipline. So to a large extent, I'm sure we're going to have a wonderful time. Once again, I thank you so much for this opportunity. Like you said, it's something I love doing. I love research. I'm passionate about research. Any opportunity I have to discuss and share my experiences in research is something I embrace with all enthusiasm. Okay, so in the next 4 weeks, we'll be having 4 classes. The first is the preambles and descriptive statistics, which we have this morning. For the next class, it's going to be correlation and chi-square. The next one will be looking at t-test and ANOVA. And lastly, we'll be talking about regressions, contingency table analysis. For today, there is, how do I put it? There are some foundations that we ought to put in place before we can start talking about any form of analysis. And that's what I meant by preambles. It's just some foundations that we need to put in perspective. And that's very important. If we don't sort out the issue of preambles, I will just be speaking to the wind and nobody will understand what we are talking about. And once we are done with the preambles, I will try to start the descriptive statistics class. Hopefully, we should be able to finish in good time so that we can look at some sample analysis using SPSS as in a live class to see what I'm talking about. And good enough, the lecture material had been sent earlier on, so I'm sure it can help us to be a bit faster since we might have gone through it. And I sure hope we have some time also to be able to entertain questions and comments. So my name is Nii Taiwo, and I'm happy to be with you all. So we just said the ball rolling. For a disclaimer, this presentation contains materials that I have referenced and adapted from various online sources. So these materials are included solely for educational and informational purposes. I don't claim ownership or original authorship of all this content sourced from external references, and full credit is due to the respective authors and creators of these works. So let's start. What is research? Because when we talk about data analysis, it's assumed that it's a fallout of our research process. I mean, we've collected data and we are thinking of how to analyze that. So let's just define research. And it's a systematic investigation, including development, testing, and evaluation, designed to discover and contribute to a body of generalizable knowledge. So the whole essence of research at the tail end is to contribute to a body of knowledge. So if you are doing a research and you are not adding new knowledge, I think it's not research. It's actually maybe a waste of time. Your research must end up with contributing to a body of knowledge. And how do we get that information? Part of it is via data analysis. And for this particular class, I'm going to be showing us the research process, and I will be working with some assumptions that we have some understanding concerning the research process. So the research normally starts with a title or a research question that has been bothering you, an observation, something you've been looking at that you want to try and get more information about. You've done a literature review and that's ascertained that your topic is novel. It's something that has some relevance, has some value that can add to the body of knowledge, and then you've gone with an hypothesis. That is definitely if you are doing something quantitative. And then we have the approach that you want to use for your design, for your research. Normally we have three approaches to research. We have the quantitative, we have the qualitative, and then we have the mixed method. And for data analysis, definitely we are working with quantitative. Remember, the title of the series is Quantitative Data Analysis. And for your research, you have done your sample size calculation, you've gotten the sampling method to use to, excuse me, to use to gather your samples. And then there's this part, which is very important, that is the variables and measurement scale. And it's one of the foundations that we need, for our data analysis. We need to identify the kinds of variables we are collecting and how they are measured. And then whatever method you use for your data collection, either an app, either questionnaire, online, Google form, survey, whatever it is. And then you end up at the data analysis phase, which is where we are supposed to be spending the next 4 weeks, after which you report your findings, and then the cycle continues over and over. It's a process that continues because you can never fill up all the knowledge gap that we have. So this is where we are going to be spending some time, but we are still going to look at this aspect, that is the variables and measurement scale, because it has a very strong influence on the type of data analysis that we do. So let's quickly talk about variables. What are variables? What's a variable? A variable is a characteristic that may assume more than one set of values. So anything that varies is a variable, something that can change form, can change position, can change quantity, can change, anything that can change, that can vary from an initial set, is what we call a variable. And once we have a variable and you can assign a numerical measure, that is the measurement scale, where you can assign a numerical measure. And I'll talk about that as we continue. So a variable, again, is any characteristics, number, or quantity that can be measured or quantified. The mere fact that it can change is what makes the variable. This term encompasses anything that can vary or change. So you can see that it's just coming over and over again, something that can vary or change. Your age today is not your age last year, so that is a variable. Your weight, as I'm talking to you now, might not be your weight by the end of today. Obviously, you will have eaten or whatever, that will have added something. So anything that can change or vary, is a variable, and it can range from simple concepts like age or height to more complex ones like satisfaction levels, quality of oral health, economic status, intelligence quotient, whatever it can be. Anything that can vary is called a variable. So these are examples of variables: height, age, your income, your position in class, occupation, your gender, educational level, types of car, your dwelling place, your location, state of origin, all manners. All those are examples of variables. And we deal with variables as researchers. 247, that's all we do. We work with variables. A variable is different from a constant. A constant remains the same, it doesn't change. Yesterday is the same, today is the same, tomorrow is the same, next tomorrow is in the same. If it is here in the north where I am based here in Jos, it's the same. When I go to maybe down south, like in Lagos, it's the same. I go to maybe an African country like Kenya, maybe Tanzania, Zimbabwe, Cameroon, Ghana, it's the same. A constant is the same. It doesn't change over time. It has a fixed value. That's a constant. It has a fixed value. So that's what differentiates a variable from a constant. Like the value of pi, this is something that we must have come across, maybe as science students growing up in school, 3.14. Although there are other digits that are behind number 4, but that number, that pi, is a constant anywhere you go. The value of pi in Nigeria is the same value of pi in Canada, is the same value of pi in US. Anywhere. It's an example of a constant. The speed of light is constant. The formula for the area of a rectangle, that's the same formula anywhere you go. The circumference of a circle, pi r squared, is the same. It's constant everywhere you go. The circle might change, the rectangle might change, but the formula remains the same. So those are examples of constants, and constants have a fixed, value. So we now go to categories of variables. Now that we know what variables are, let's talk about the different categories of variables that we have. There are 2. Number 1 is quantitative. Quant, that means something that you can measure, quantity. Quantitative or numerical variables. And the second one is qualitative or categorical variables. And we'll quickly look at the 2 types, as we continue. So for the quantitative variables, It's a variable that can be measured, very important, numerically, or you can count it, such as age, height, weight, number of people, number of participants, number of schools, number of whatever it is, something you can measure, something you can count. That is the quantitative part of it. Quantitative variable. They represent a measurable quantity. For example, when we speak of population of a district, population of a country, population of maybe a region, we are talking about the number of people in that district or in that population, in that region. So we can count that number. So population as a term is a variable. It's something we can count. Weight is something we can measure. Blood pressure is something we can measure. Temperature is something we can measure. So all these are quantitative variables. And the quantitative variable can either be continuous or discrete. Continuous or discrete. So just for an example, anything that you measure that can have a decimal point, that's something that can have an infinite number of values. As long as you can have a decimal point or something that can be in fractions, we call it a continuous variable. A discrete variable, on the other side, is something that can only be in whole numbers. For example, if I talk about the number of people in this presentation now, maybe 200, we cannot have 200.1 persons. There's nothing like 0.1 people. You understand? So we talk of discrete variables for something that are whole numbers, something that you can count. Whereas for the continuous is something that you can measure. You can measure it. And anything you measure has the possibility of having a decimal point. So like I said, a variable is continuous if it can assume an infinite number of real values. That is, if it can have decimal points, we call it continuous. Weight, height, temperature, pressure, distance, all manners, anything that can have a decimal point, even performance in class. If you are having an exam over 100%, somebody can have 90.5%, can have 30.2%. As long as you can have a decimal point, we call that kind of variable continuous. In general, all measurements, whatever it might be, are continuous variables. Another name for continuous variable is what we call interval variables. So as opposed to a continuous variable, a discrete variable can only take a finite number of real values. Remember, for the continuous is infinite. A discrete variable is finite. These are variables that can be counted. Whole numbers. They are whole numbers. They are not in fractions. Okay. Example is the eggs laid by hens, the number of children in a family, the number of patients in the clinic, number of students in the class, the number of people in this presentation, the population of the country, a district, a region, a locality, anything that you can count, is a discrete variable. The number of cars, the number of houses. You don't have things that are in fraction under discrete variables. Okay, that being said, now let's talk quickly about the qualitative variables. Remember, we are trying to ascertain this type of variables because they are needed, when we talk about analysis, and you understand as we continue. A qualitative variable, also called categorical, is one that cannot be measured. You can't measure it, but it's still a variable for which a response can be put in a specified category. These categories must either be mutually exclusive and exhaustive, not just or, both and exhaustive. So what do we mean when we say mutually exclusive? That means that all the possible survey responses should belong to only one category. Let me give an example. So we are talking about educational status. It's either somebody has no education at all, it might be a primary level, secondary level, or tertiary level education. So, that is all the possible survey response we should have, and somebody should belong to that one category. So exclusive means that each possible survey response should belong to only one category. You cannot belong to two categories out of all that I've stated here. It's either you have a primary level education, a secondary level, or a tertiary level. You can't have both. So you must just have one, although a tertiary level encompasses others, but that is the level that you have as at the time we are asking the question. Exhaustive will mean that we don't have any other option outside, what we have here. So it should include all possible answerable responses. In the past, when we talk about gender, it was usually male and female. But now it's no longer exhaustive because we now have all manners of people identifying with different kind of gender identity. So now we might need to expand that options if we are trying to like get something to do with gender and so on. You know, occupation, marital status, all manners, type of cars, type of house, you know, the location you are staying, they are all variables. Those ones are not something you can measure. These are things you can give a category, and that is why they are qualitative. Now, for qualitative variables, they can either be ordinal or they are nominal. Ordinal or nominal. When we say ordinal, it's something that is ordered or arranged in a particular way. Sometimes they are called rank variables. Rank ordered variables. It's either it's an ascending order or it's in a descending order. Remember, it's still qualitative. And then we have the nominal. So this is for the ordinal variable. This is for the ordinal variable, and the other one is for the nominal variable, the one that is not ordered. Okay, so for the ordinal variable, like I said earlier on, it's also called rank ordered variable. And some examples of these variables are like the position in a class. You have a student class with students. There's a way you order their performance. First, second, third, down to the last. That's an example of an ordinal variable. Socioeconomic status. People can be in the low income, middle income, or high income. That's another type of variable that is ordinal and qualitative. Now, you should note that these do not express a degree of magnitude. They don't express a degree of magnitude. What do I mean? For example, this position in the class, the person that scored came first, maybe 70%. The person that came second might be 50%, and the third person might even be 49%. So it's not as if there's a uniform magnitude in between. It's just a label to let us know that, okay, this one is higher than this one is higher than this, and it continues like that. There are some kind of natural ordering, you know, like we can talk about the stage of pregnancy, you know, first trimester, second trimester, third trimester. We can talk about cancer stages, stage 1, stage 2, stage 3, stage 4, Likert scales, educational status, like I gave earlier on. For example, Likert scale, let me just give that as an example. Many of us will have come across that in many things we do. You will see some questions where, you know, the options are in Likert scale, something like strongly disagree, you know, neutral, agree, strongly agree. As you can see, there's a kind of ordering here, you know, and depending on how you want to code them, it can either be on this side or it can either be on this side. All I'm trying to say is that it's ordered in a particular form. And that's a good example of an ordinal variable. Now, for the nominal variable, it's just a label. It's a name or a category, you know, that you assign to variables. For example, gender, sex is a nominal variable. It doesn't mean that male is greater than female, neither does it mean that female is less than male or whatever. The color of a clothes is an example of nominal variable. Yellow is not better than blue, green is not better than red. It's just a label. It's just, you know, something you use to assign, you know, to a variable. Unlike the ordinal variable, there is no natural ordering of the set of possible names or categories for a nominal variable. Is just a label. Location, I am here in Nigeria. Somebody is in Tanzania. Somebody is in UK. Somebody is in Ghana, Cameroon. They are all nominal because it doesn't make Ghana superior to Nigeria, nor is Nigeria superior to Kenya. Just a label. And we come across all these kind of labels, you know, when we do our studies in different areas. So for a summary of our variables, variables can be quantitative or numeric, or qualitative or categorical. For the quantitative, we said it's something that can be measured or counted. For the measured part is continuous. The one for counting is the district. For the qualitative or categorical, we said we can have the one that's ordinal or rank ordered, either ascending or descending. The one that is nominal, which is just a label. That is for the summary of the variables. Okay, so we need to also mention some other types of variables for us to just understand, because we'll be mentioning them in the course of this series. Number one is binary variables. When we say something is binary, it means it's a kind of nominal variable with just two levels of measurements. We call them binary variables, a nominal variable with just two levels. What do I mean by two levels? You know, it can occur in one of two possible states. Like we can have a question and the response to the question is yes or no, nothing more than that. That makes it a binary variable, dead or alive, present or absent, true or false, you know, here or there, you know, whatever it is that has only two possible observations, we call it a binary variable. Another name for binary variable is dichotomous. Dichotomous. Why are these variables important? There are specific analyses that are based on binary variables. So you must be able to identify your data to be sure that it's a variable that will apply for that kind of analysis. We have what we call a dependent variable. And for a definition, is the presumed effect in an experimental study. Presumed effect in an experimental study. And the values of this dependent variable is dependent on the independent variable. So, frankly, you know, a dependent variable is only used when you are doing an experiment. It doesn't mean that people don't use it for other kind of non-experimental studies, but frankly speaking, what you are doing is an experiment. We term it a dependent variable. You know, normally we have this notation X having an effect of Y. So let's say that I'm doing an experiment now with this class, looking at the impact of this lecture on your knowledge of data analysis. You know, so it's an experiment. I've gathered all of us together and I'm giving us this lecture and I want to look at the impact, you know, so I will say that a class on data analysis, and then I can say knowledge. So our knowledge level on data analysis. Instead of saying class, let me just say lecture. So lecture on data analysis. So I'm giving this lecture and I want to look at the effect on our knowledge of data analysis. So knowledge of data analysis here is my dependent variable because it's dependent on the lecture I'm giving. So the lecture here now is the independent variable. I hope we get it. So it's just a kind of relationship, but we call them dependent, independent, if it is an experiment. There are other terminologies, synonyms that we use if what we are doing is not an experiment, and we'll see it as we continue. So like I said in the previous slide, the independent variable is the presumed cause. For the dependent variable is the effect. So the presumed cause in an experimental study. All other variables that may impact the dependent variable are controlled, and the values of the independent variable is under the experimenter or the researcher's control. So like the example I gave in the previous slide, I am the researcher, I'm giving the lecture, and I want to look at the impact of that lecture, you know, on your knowledge of data analysis. Then we have another name for independent variable. It can also be called a manipulated variable. It can be called a treatment variable. It can be called a predictor variable. But these terms are actually better used if you are doing something that is not an experiment. Predictor variable. Let me give an example. So I'm looking at the influence of socio-economic status on our health, maybe quality of health. So this is my X, this is my Y. Looking at the influence of socio-economic status on the quality of health. Now, my quality of health here is an outcome variable. Outcome variable. If it was an experiment, I would have said dependent variable. But because this is not an experiment, I'm just checking people's data information, and I'm trying to assess that impact. That's why I'm calling it an outcome variable. Whereas on this other side, my socioeconomic status is my predictor variable. You know, another name for that is manipulated variable. Another name is treatment variable. All I'm trying to say is that people use these terms synonymously, but in actual fact, you know, if you want to show that you have an edge above just the general knowledge, dependent variable, independent variable should be used when you are doing an experiment. But nonetheless, I mean, I can say that my socioeconomic status here is an independent variable, and I can say that my quality of health here is my dependent variable. Why am I saying that? In softwares like SPSS, SPSS will not say that one is an experiment, one is not experiment. I think SPSS will just give you dependent, independent. So you should know which one of your variable is the independent, which one is dependent. But you should know that there are two different variables, one on the X side, the other one on the Y side. Then there's another variable we call the intervening variable. Sometimes we have a relationship, but that relationship is not just on the surface. There's something that is explaining that relationship. And I will use that same example I used earlier on, socioeconomic status. What is the influence on the quality of health? This is the research question. However, this particular research question or this particular relationship can be explained by another variable that is not in this relationship. So that means that the more money you have, it's most likely, it's not just having money that gives rise to a better quality of life. If you have money, you might be able to afford health care because you are rich. So this health care from this particular relationship is what we call the intervening variable. Sometimes it is called explanatory variable or mediating variable. Actually, the healthcare here is what explains why your quality of health is better. Because the more money you have, the more healthcare you can afford, and then the better your quality of health. So it's a kind of variable that explains a relationship, or it provides a causal link between other variables. We call it intervening variables. Another name is mediating variable, another name is intermediary variable. And then we have, I've mentioned this one earlier on, the predictor variable, which is like the independent variable. And then I spoke about the outcome variable, which is like the dependent variable. It's just like a kind of synonym, depending on the kind of study you are doing, so that is for that. Then we have, I wanted to talk about, and I think I should talk about it here. Then we have another kind of variable, it's not on this slide here. We call it the confounding variable. Confounding variable is something that, it's not an explanatory variable, but it has an effect both on the independent variable and the dependent variable. We call it the confounding variable. And in this particular example I have here, remember, this is my independent variable, socioeconomic status. My dependent variable here is quality of health. And we have up here my mediating variable or explanatory variable. There's another variable that we can have here. Let me say educational status. Educational status. And I'm going to do something here, and I want you to be very observant. In this particular variable, look at the direction of my arrows, unlike what I have for the mediating variable. For the mediating variable, you will notice that the arrows follow a particular line. It starts from the independent variable and ends on the dependent variable. But for the educational status, you will notice that it is like in between, and then it has one having an effect on the dependent variable, another one having an effect on the independent variable. So the more your educational level, the higher the chances of having a higher socioeconomic status, and the more your educational level, the higher the chances of having a better quality of health, because you now understand what you need to do and not to do to live a healthier life. We call that kind of variable a confounding variable because it affects both the dependent and the independent simultaneously. Unlike the healthcare, which is a mediating variable, is just in the explanatory pathway, in the causal link. It's just in between. It doesn't affect. So healthcare here does not affect the socioeconomic status, rather it is on the way of affecting the dependent variable, which is the quality of health. That is about the confounding variable. I've discussed this. Now, we quickly look at measurement scale, which is another preamble that we need to sort out very fast before we start talking about our analysis. Remember, one of the definitions of variable is something that can vary to which a measurement or can be assigned. So that measurement in that definition is the measurement scale. And it just means assignment of numbers to variables, assignment of numbers to variables. In statistics, please look at this, very cardinal. In any kind of statistics, the kind of descriptive statistics and inferential statistics, depends on the measurement scale of the variables concerned. The kind of descriptive statistics and the appropriate inferential statistics, that is the test of significance, depends on the measurement scale of the variables that you have. So measurement scale are used to quantify variables. And below are the properties of a measurement scale. It can have an identity, it can have a magnitude, a uniform interval, and a minimum value. Identity, magnitude, uniform interval, and a minimum value. Each scale, for identity, each scale has a unique meaning, and I'm going to explain it as we continue. For magnitude, there's a uniform increase in value from one end to the other. Interval, that's uniform interval, the calibration of measurement is equal throughout the scale, and for a minimum value, that means there should be a minimum value for which no value exists. A minimum value below which no value exists. For measurement scale, there are 4 types. We have the nominal scale, the ordinal scale, the interval scale, and the ratio scale. Even from here, I can tell you that the nominal scale and the ordinal scale, from their name here, they are for qualitative variables, while the interval scale and ratio scale are for quantitative variables. I mean, from the name that we have there. So let's look at the nominal scale. It's the lowest scale of measurement. And what it does is just it gives an identity. And with the numbers we assign to these variables are just labels. They are just labels, nothing more, to differentiate one response from the other. So you have a questionnaire, and part of your responses are yes and no, present or absent, true or false, whatever it is. You know that you have to code, that's the word, you code these responses for you to be able to analyze them. So we can say yes is 1, no is 2. We can say yes is 0 and no is 4. We can say yes is 11 and no is 53. All these numbers mean nothing apart from just to identify our response. So if we have numbers like this, that does not mean that you can find the mean of yes or the mean of no. So you need to know what those numbers mean. That's the measurement scale. It's just to identify. If it's a nominal variable, your measurement scale is a nominal scale. The assignment of this number is not important. It's just for identifying and to label the responses. I can choose to say that my yes is 1 million. And I can say my no is just number 3. It doesn't make any difference. It's just a label, for that variable. So that nominal scale is just identity, okay? For the ordinal scale, apart from identity, remember our ordinal variable, there's magnitude, is rank ordered. It's either they are going ascending or they are descending. Here, the assignment of the number is important, but the magnitude of the difference cannot be quantified. The assignment of the number is not just a label, it is important, but the magnitude of the difference cannot be quantified. Like I spoke earlier on about position in a class, position in a race, it's important that this person is first. If we have people with this from a class, it shows something. It's important. Somebody who is first is obviously first. He has a higher score than the second person and the third person. But what is the difference between the first and second? That is the magnitude of difference. We cannot quantify it. But we know that there's a first position, there's a second position, there's a third position. So anything that you have in ordinal scale is from ordinal type of qualitative variable. And we quote them or we measure them using an ordinal scale. We quote them or measure them using an ordinal scale. Now we go to the interval scale. Apart from being ordered, the distance on interval between subjects or objects increases with common and constant units for all members of the ordered set. Here, the distance is meaningful. So there is, how do I put it? That range, the distance between one value and the other value is meaningful. An interval scale satisfies identity, magnitude, and uniform interval, but does not have a minimum value. So that value 0 is arbitrary. It does not exist in a minimum, in an interval scale. There exists an arbitrary zero. That is, the presence of zero does not mean the complete absence of the property being measured. A very good example of an interval scale is temperature. You know, temperature, when we say 0 degrees centigrade, it doesn't mean that there's no temperature. It actually means that it's freezing. You know, so 0 does not mean absence of what is being measured. 0 is arbitrary in an interval scale. An interval scale is not too common in what we do in our research work. So most of our scale is not actually measured on interval scale. However, we do have, you know, some situations where we use interval scale. But that is the cardinal difference between interval scale and the next scale, which is the ratio scale. The absence of a true zero, that is what makes interval scale an interval scale. The zero is arbitrary. You know, another example is pH. You know, a pH of 0 does not mean that there's no acidity or alkalinity. You know, it just shows that particular level. Or a number line, good. You know, when we have a number line, we have 0, then we have 1, 2, 3, 4, 5, and then we have on the negative also. So 0 does not mean absence. It just means the middle point, like a scale. So 0 is something, it doesn't mean that it doesn't exist in the number line. That's an example of an interval scale also. Now, for the ratio scale, and this is the most important measurement scale that has all the meaning, is the most important measurement scale. You know, here we have absolute zero, not arbitrary zero. The zero value on a ratio scale is not arbitrary. If we say 0, 0. If we say, example, work done, we can say work done is 0. That means nothing has been done. That means that there is an absence, a real absence. Nothing has been done. Or if I'm supposed to go to maybe to the room and I say distance covered 0 centimeter, that means I have not moved from where I was sitting. It has, you know, a meaning showing absence of what was being measured. Most physical quantities, weight, height, energy, are measured using this scale. In other words, all measurement and count, all measurement and count, all measurement and count, I'm repeating it for us to grab it. This is quantitative variables, if you remember. All measurement and count are based on ratio scale. So any variable that is quantitative, we normally use the ratio scale as a measurement scale for addressing them and for their analysis. Please don't forget that all measurement and count are based on ratio scale. And this ratio scale is where you can add, you can divide, you can multiply, you can subtract, you can do all forms of mathematical calculation because the 0 there is not arbitrary. So all mathematical calculations apply for a ratio scale. That's the same reason why you cannot add or divide or multiply a nominal scale because they are just basically labels. But here, ratio scale, all measurement and count are based on ratio scale. So to just summarize all I've been talking about, for the hierarchy of the levels, the nominal scale is just attributes are only named, is the weakest. You go to the next one, which is the ordinal level. Here, the attributes can be ordered, either ascending or descending. For the interval, the distance is meaningful, but it's an arbitrary 0. And for the ratio, there is an absolute 0, not arbitrary, it's absolute. And then we quickly talk about data. And data is a collection of observation or measurement used to analyze and make decisions. Okay? Data can be numerical, like count or measurement, or categorical, like label or classification. So from what I've just said in this second bullet point, data can be quantitative or data can be qualitative. That's all I'm trying to say. And you can see that it says, therefore, data is a set of values of qualitative or quantitative variables. And data is the starting point for analysis and is examined, manipulated, and interpreted to draw conclusions or to make predictions. So I will give us a small example now. Let's take the variable age. That's a variable age. So if I'm to collect or I'm to request for the age of all of us in this presentation, and let's say we have about 350 of us on this presentation, by the time I collect the age of all of us, that's 350, what I have is what we call a data. Remember, it's a collection. So the collection of all that particular variable makes it a data. Now, from that data, if I can like harness it, that, okay, from the male, I have so number of data, data. From the female, I have so number of people with their age. Or I can say that there are 17 that are less than 20, there are maybe between 18 to like 100 that are between 20 and 50, and something like that. That particular narration is information. That particular narration is information. Remember, the total collection of the variable is data, but when you are trying to like categorize or group them, it makes it an information. But when I now start saying the mean age is so and so, the standard deviation is so and so, at that level, that is statistics. I just want us to know the difference between data, information, and statistics. So data is just the collection of observation, which can be quantitative or qualitative. Information is just trying to like, make it presentable in narration form. Statistics is when you apply some calculations on them. So data is the starting point for analysis, okay? And then being that data can be quantitative or qualitative, their groups or their types also follow the definition of variables. So data can be quantitative or numeric, qualitative or categorical, just following our classification of variables, if you remember. So we can have continuous data, we can have discrete data, we can have nominal data, we can have ordinal data. Remember, it's just the collection of variables, so it follows the same path. Now, when we are talking about analysis strategy, it follows three approach. It can be either univariate, when you are just working on one variable. For example, I just spoke about age. So if all I'm collecting for my analysis for my work is just age, is one variable. So my analysis will follow the analysis of just one variable, that is age. But I might be working between, maybe I might collect two variables, age and maybe weight. I want to look at the relationship between age and weight. And I'm collecting only two variables, that's age and weight. Or I might be collecting so many variables. I might be collecting age, data on age, weight, height, maybe gender, occupation, etc. And this is where we normally collect data from, because our questionnaire is not just asking one variable. It's asking so many questions, and so many questions means so many variables, So we can have a multivariate analysis. So our strategy can be based on one variable, a bivariate variable analysis, where we have two variables, or multivariate. However, please listen to this. However, when we even have multivariate variables, you might choose to analyze only one of the variables for a purpose. So somehow it still falls to like analyzing a univariate variable. All I'm trying to say is that you might have a questionnaire, and in that questionnaire, you just want to know what is the prevalence of a particular condition, or you want to know what is the mean of a particular variable. So that still falls back to univariate variable. The analysis of a univariate variable is actually what we call a descriptive statistics, because descriptive statistics normally work with one variable most of the time, but sometimes it can be combined, but most of the time it works with one variable. So let's talk about descriptive statistics, which more or less is like the start point of our discussion this morning. And I'm going to try and be a bit fast. It's not so new to us as a concept. The areas that might be a bit new are the areas that we emphasize, so to say, but it's something that we have had over and over, but there are areas you think you knew that might be coming to you afresh. So the descriptive statistics refers to a set of methods we use to summarize and describe the main features of a data set, something like the central tendency, variability, and distribution. They provide an overview of the data and help us identify patterns and relationships. So the descriptive statistics helps you to explain to other people what is happening in your data. So you have collected your data en masse. You want people to understand what is happening in your data. You describe it to the people. And before we can begin to describe data, we need to decide what sort of data we have. Recall what was said about data, that it can be qualitative or it can be quantitative. And for quantitative, it can be continuous or discrete. It can be nominal or ordinal. Please don't forget this analysis. It's very key. in all that we are going to be talking about. And we also spoke about the measurement scale that can be nominal, ordinal, interval, or ratio. These two are for qualitative. This one basically is for quantitative. You understand? So once you remember that, it makes our discussion faster. Now, for the univariate analysis, remember this, we said something about analysis strategy or the approach to analysis. Now, you can now see where the issue of types of variable comes in. For our analysis, you must know the type of variable you are collecting. If your variable is continuous, we can talk about central tendency, mean, median, mode. We can talk about measures of dispersion, that's variation, variance, standard deviation, range, percentile, interquartile range. We can talk about the distribution, is it nominal, normal, uniform, or exponential. We can talk about some kind of graphs that you can use for a continuous variable, something like histogram, box plot, stem plot, dot plot, line chart, time series plot. So if your variable is categorical on the other side, that's where we talk about frequency tables. We talk about the plot, the bar graph, the pie graph, the Pareto graph, and all. So please, that is why I had to take some time to put those preambles in place, as a foundation. You must know the type of variable that you have to determine the kind of descriptive analysis that you are going to use. So by summarizing information, descriptive statistics speed up and simplify comprehension of a group's characteristics. Inferential statistics, on the other hand, which is what we start looking at from next week, we allow researchers to make decisions or inferences by interpreting data patterns. So we start talking about inferential statistics, correlation chi-square, t-test, ANOVA. That's from next week going forward. So for an illustration, we have here an example of data. We have a data for class A, we have a data for class B, and we have their weights. For example, just a weight. I mean, these weights are outrageous, but it's just for classwork. So we have this weight for 13 students in class A, 13 students in class B. And the question is, which group is heavier? It's going to be difficult for you to just look on this and say, this is heavier than that. It's going to be challenging. So when we now find the average weight, you can see that they are more or less roughly the same, 110.2 for B, 110.5 for class A. And that is how descriptive statistics helps. So looking at the raw data, you might not be able to know what is going on, but when you describe it either by any of the method, it gives you an idea. So going back, looking at all these figures, this is just data. It's difficult to know which class might be heavier or not. But when we have found the average, it's easier now. So when we talk of descriptive statistics, it's basically it's either you are organizing your data or you are summarizing your data. Organizing your data or summarizing. When we organize, you can organize your data in tables or graphs. When you are summarizing, it can be either the measures of central tendency. So let's assume this is our collection of data. Measures of central tendency means how do the data, tend towards the middle of the data. That's measures of central tendency. On the other side, measures of dispersion is from the center, that's variation. How do the center, the data move away from the middle? So this one is the central tendency, this one is variation, that's measures of dispersion. So, and remember, we spoke about the univariate analysis. And when we are talking about measures of central tendency or dispersion, it's actually going to be here because these are the two that has those, this is central tendency dispersion. Then we have the ones for the plot just to organize the data. So just like a picture, descriptive statistics, you can either organize your data or you can summarize it. For the organizing of your data, it can be in forms of tables or graphs. To summarize it, it can be central tendency or variation. So let's talk about the tables. The tables can be used for categorical and ordinal data. Now, when I say categorical, ordinal data, nominal data, now you understand because those are the terms we'll be using. It can also be used for continuous data. You can see that that's why the emphasis on that preamble, And then we have graphs, the pie chart, the bar chart, stem and leaf plot, frequency polygon. So let's go to tables. And table is straightforward. It's just a frequency distribution, that displays the frequency of various outcomes in the table. each entry on the table contains a frequency, and on the other side, we have either the distribution, either in tallies, in numbers, in frequency, or in percentages. The objective of a frequency distribution is to provide insights about the data that cannot be quickly obtained by looking at the original data. So you just provide an insight. This is an example. For the weight of students, we have here the weight, going down here, and it's telling us the frequency of the weight. So we can see from here that we have 2 of them with weight 93 kilogram, another 2 of them here with weight 131 kilogram. And this is the percentage of those weights, among the population. And we have the total number of students that we have here, 8.3 here, 8.3 here, to just denote those that have 2 frequency. And that's just that for a table. This is another example for when we have group frequency. Now, look at this particular example, and I put this one here deliberately. The first class interval says 15 to 25, and we have 60 here. And the second one says 25 to 35. No, there's an error here. We have 25 here, we have 25 here. So if there's 25 among our frequency, among our data, where will it fall? So this is an example of a wrong class interval. This ideally should have been 26 to 35, 36 to 45, 46 to 55, 56, to allow all the variables or observations to fall in specific group interval. Very important. If you add up everything here, I think it will give you 150, so it shows that we can use the table also to, summarize our data. And we have the issue of tally. I'm sure you are aware of tally. Here it shows that there's 0, nothing is there. Tally is just counting the lines. This one is 3, and that's why you have it here. When you have 4 and a line cross across, that makes it 5. So if I have another set of tally here, this will have been 10 instead of 5, and that's just tally. And as you can see here, the class interval represents all the groups very well. 0 to 4, 5 to 9, 10 to 14 is not overlapping like the one on the other side. That's a tally, and we are aware of that. And this is another example, but we are talking about cumulative frequency here. Now look at here, these are the number of books read in a month. These are the frequencies of what is read in a month. For a cumulative frequency, for each succeeding succession in the lines, you just add the previous frequency to make it cumulative. So the number of books read in a month is 2. The frequency is 1. Those who read 3 definitely has read, they read 2 before they could go on to make it 3. And cumulatively, you are just adding the 1 they read with their own to give you 4. And then the same thing goes on like that. Those who read 4 books, their frequency is 5. 5 plus 4 gives you 9. 9 plus 2 for the number 5, 11, on and on, and 12. This 12 is the total number of people. That's the cumulative frequency. The same thing applies for class interval here. For those between 1 and 5, they were 2. Those between 6 and 10, they were 6, and they were 4. 4 plus 2 gives us 6. 2 plus 6 gives us 8. 1 plus 8 gives us 9. So the total number of people here is 9. That's cumulative frequency. It's a straightforward table, nothing highfalutin there. And then we have the relative frequency table. Relative frequency is just like taking the particular frequency and dividing it by the total number to know the particular percentage they occupy. So we have our group here, 1, 2, 3 to 6, and we have the frequency here. And if you add the frequency, you will get 16. So what is there for like group number 1? We want to know the relative frequency. It's just going to be 2 over 16 times 100, or if you multiply by 100, that's when it gives you the percentage. But if you just say 2 over 16, it just gives you the fraction. And that's what we have in this area here. The one that is 4, like number 3 and number 5, is 4 over 16, 4 over 16. Once you multiply it out by 100, it gives you the percentage. So that's just the relative frequency among the total frequency. That's relative frequency. And that can also be done for a class interval. As you see here, it's relative frequency, but to get the percentage, we multiply each one by 100, and then it will give us a percentage. And once you add everything, it will give you 100% also. That's just for table and straightforward. And that's just table as a concept of descriptive statistics is just to organize your data. You can find the frequency, you can find the tally, you can find the cumulative frequency, you can find the relative frequency, which I've just shown us. So let's go to the issue of graphs. And we are going to start with histogram. Histogram is used to display frequency distributions of interval and ratio level data. Are you seeing where all those preambles coming now? So you must know the kind of data you have. So if your data is something that is ratio level or interval level, that means your data must have been quantitative for you to talk about using histogram. So histogram looks like a bar with no spaces between them. We have come across all this coming up as students, and you cannot use it to display information of more than one variable. The variable of interest is placed on the horizontal axis, that's the horizontal axis, and then that's your vertical axis. A rectangle is drawn above each class interval. The height is corresponding to the frequency or the relative frequency or the percent frequency. And I'm going to show an example. So that's an example of a histogram. That's for a weight of maybe some group of students. I want you to notice that there is no space in between the rectangles. There's no space, very important place. So this is a histogram, and it's used for quantitative variables. That's another histogram. This is two different histograms just put together to make it more beautiful. This is for blood pressure. The one above is for the systolic blood pressure. The one beneath is for the diastolic blood pressure, just to make it look a bit artistic. This is another histogram, weight of students, and you can see here the frequency, and we have the class interval here, and you can see how the weight is arranged. Another histogram here. And now we are going to be talking about some concepts, of histogram. We can say a histogram is symmetric. If you look at this particular histogram, let's assume we divide it into two equal halves. It looks like the side on the left mirrors the image on the one on the right. We call that symmetric, something like that. You understand? So that's a symmetric histogram. A histogram can be moderately skewed to the left. If you look at this particular histogram, it tends to be longer on the left side compared to the right side. Some kind of data can give you that, like exam scores. Many people tend to have lower scores, only a few tend to have higher scores. It can be moderately skewed to the right also, just the opposite of the previous one. That's another type of a histogram. Or it can be very highly skewed, like our income level. If you want to take our income level, you can see that some people have very high income level. Most of us have lower income level. Those are all types of histogram. And that skewness, which I was talking about, is a measure of the asymmetry of a distribution. A normal distribution has a skewness of 0. That means that it is one side is the mirror image of the other. A normal histogram has a skewness of 0. Positive skewness means that you have longer right tail. Negative skewness means you have longer left tail. That's just that. You might do a normal distribution and see this skewness, but remember, that a normal distribution has a skewness value of 0. Skewness can be calculated, with your data, but we're not going to do that. It's just for you to know that there's a formula for calculating skewness, and that's the formula. Our class for this morning is not concerning the calculation, and like I said earlier on, these are different shapes of histogram. This one is a normal, where it is symmetric. I just think I will be able to do something like that. Yeah, you can see that. That's a normal skewness. This one is right skew. This one is left skew. So that's for that. We'll talk about the shape of the peak of the arrangement of the histogram. So, and that one is called a kurtosis. Kurtosis is a measure of the extent to which observations cluster around the central point. For a normal distribution, the value of the kurtosis is 0. And then we have what we call a leptokurtic, where the values are more peaked, that's close together. Let me go to the previous slide. This one is a leptokurtic. As you can see, my distribution here is peaked. It's having like a sharp dome shape, unlike this one that is a bit shallow. This one is the platykurtic. So you can do your histogram or your normal distribution and check the kurtosis. It can either be leptocortic or platycortic. Platycortic data are flatter and more dispersed along the x-axis, whereas the leptocortic are more peaked. They are just like a dome-shaped. Okay, it also has its own formula. We are not going to be working on that, but just for you to know that once you have your data, you can find the mean and you can just like arrange for substituting the values to get the value of kurtosis. The normal distribution, our kurtosis is 0. Normal distribution, our skewness is also 0. So like I said, we have the leptocortic and we have the platycortic. One way you can easily remember this is just look at this word platy and just say flat. I think that's how I used to remember it, flat. So once it is platycortic, that means that the kurtosis is flatter, unlike the leptocortic that is peaked, okay? So this is an example of a variable. For an example, age, in our softwares, you can run the descriptive statistics. But what I want to bring out is the kurtosis and the skewness. If you look at here, the kurtosis, there's a negative mark there. That minus shows that it is flat. It is platycortic. It shows that it is flat. And for the skewness, you can see that our skewness is 0.3. It's supposed to be 0, actually. You understand? But it just shows that for this particular one, there is a slight right skewness. Slight right skewness. It's not so bad, but our kurtosis shows that it is flat. And then we have the other measures of a central tendency. I will talk about those ones as we continue. That's a normal distribution. As you can see, it looks like a mirror image. It looks like a mirror image of the other side. Then there's this thing about frequency polygon. They are a graphical device for understanding the shapes of distribution. Remember the shapes of distribution, we said it can either be skewed or we can have kurtosis. It is a frequency polygon that makes it easy for us to see that shape. They serve the same purpose as histogram, but especially helpful when you are comparing data sets. Frequency polygons are also a good choice for displaying the cumulative frequency of data sets. So this is an example of a frequency polygon. Number one, look at it. These blue parts, these are the histogram itself. Now, if you look at the histogram very well, at the midpoint, of the tip of the histogram, the midpoint, you have a dot there, and joining the line of the dot is what we call the frequency polygon. It's clearer on this particular histogram. So you can see it goes from the middle of A down up there, C, D, E. That is the frequency polygon. It's just like joining the midpoint of the histogram and then looking at the shape of the distribution. This is another example of a frequency polygon, to let you see the shape of the distribution. Now, this is another example of a frequency polygon with the histogram removed and the line superimposed on it. So this is a frequency polygon with the histogram removed to just let you have an idea of the shape of the distribution, knowing fully well that those between like 85 here, they have the highest score of about 40. This is another example of a frequency polygon. And then these are two frequency polygons just like superimposed on each other, to compare the presentation or the distribution. We have a large target and we have a small target. Those frequency polygon for us to see how it looks like. Then we talk about a bar chart. And please look at this one. A bar chart is used to display nominal and or ordinal data. That is qualitative variables. Qualitative variables. A single bar chart can present two or more representations. They have spaces between the bars, unlike in histogram where there are no spaces. The bars are separated to emphasize that they are in categories. So remember, qualitative variables or categorical variables. That's why we use bar chart. The height of each bar is proportional to the frequency or percentage of the category. So this is an example of a bar chart. And it's comparing two students. We have home students and international students for men, for women, and for different years. So the blue here is the British home students, the red is the international student. So I can see clearly that there are spaces in between the, the bars to denote that these ones are bar chart, unlike the histogram. And from here, we can quickly say, let me just give an example. So for year 2010, and for year 2010, we can look at for men, comparing them with women. How many home students or which one were more for year 2010? For men, it's close to like maybe 38 here. And for women, for the home students, it's about maybe 34, 33. So invariably from this chart, you can quickly picture and see which one is better or which one is more. So it has like described the data for different years, for different groups, for different categories. And that's one beautiful thing with bar charts. This is another example of bar chart. They come with different designs. You know, this one is a composite bar chart. This particular one is a composite bar chart combining two different population or groups on a chart. And that's another example here from this. Just looking at this particular chart, we can say the yellow color has more frequency or more choice among the children. This is another example of a bar chart. Remember, there are spaces in between. And this is an example of a bar chart with a cumulative percentage, which we did in our table. We call it a Pareto diagram. So you have your bar chart because you can see that the spaces are in between. And then remember, cumulative frequency for group A, we have maybe 45 as the percentage. You add the frequency to that of group B, on and on till you have it added to the one of group G, making it 100%. So it's just a combination of the frequency and the cumulative frequency. We call that a Pareto diagram. You'll be seeing it in some literatures or some articles. It just makes it look a bit scientific and beautiful, but there's really nothing there. It's just frequency and cumulative frequency, Pareto diagram. And then a pie chart, also used for showing differences in frequency or percentages among categories. A pie chart and a bar chart are both used for nominal and ordinal data or variables. Very important. You can now segment, shade the different segments for us to be able to see them differently. It's usually used to describe a single distribution, but can be used to describe two or more to compare distributions. You first have your circle drawn, and then you have the relative frequency divided, by 360 for you to have the particular proportion that those frequencies will occupy. We have done this, it's just like a reminder. So that's an example of a pie chart. Looking at this, without going far, we can see that Germany has the highest proportion. The least is from Australia. And then these are two different pie charts, that we can use to compare, for the same population. So we have the population in 1998 and the same population into year 2000. If you look at this particular one, that's all other countries. In 1998, they occupied 29.4. In year 2007, 29.7. So there's a slight increase. That's the pie chart. And you can see they have different coloration to identify the different categories. Okay? This is another pie chart looking like a donut. It's just another design, okay? And just to have a small class example for us to look at about a fast food outlet. So customers visiting a fast food outlet were asked to rate the quality of their experience as either being excellent, above average, average, below average, or poor. And this is the rating provided by a sample of 20 customers. From here, we have seen that our data type, our variable type is ordinal. You can see that there's an ascending or descending rate. Excellent, above average, average, below average, or poor. So it's descending. That makes it ordinal. And what we have here, based on what I had told us earlier on, this is what we call data. And it's just like scattered. It's difficult for you to be able to make sense out of what we have here. So this is data, and this kind of data is following an ordinal fashion. So we can put it on the table, and as you can see there, 4 is 2. So from here, from the table, we can see that above average actually has the best, the highest frequency. Going back to this previous slide, you might see it here, but this is just because we have 20. What if it is 200? That would be difficult. So making it in a table form brings it out easily. That's it there. And then we can have the relative frequency. Remember, relative frequency is just having your frequency divided by the total. So from here, our relative frequency will be 2. This one will be 2 over 20. This is 3 over 20. This is 5 over 20, 9 over 20, 1 over 20. And whatever value you have there as relative. You can then multiply it out by 100 to have the percentage, which is what we have here. That's relative frequency. We can have it out as a bar graph or a bar chart. Remember, it is grouped for ordinal. That is why there is spaces in between them. And even from the bar graph, our above average has the highest frequency. And I mean, it's obvious from there. Or we can have it as a pie chart where above average is still showing that it has, the highest frequency of 45% compared to the others. So that's just an example of descriptive statistics using the table and the chart. Then we have what we call a stem and leaf plot. A stem and leaf plot is a special table where each data value is split into a stem, that's the first digit or digits, and a leaf, usually the last digit. So let's start from this side. We have numbers 120 to 129. Our stem is going to be 1 and 2 because that is the one that is similar among all the numbers. So this is 120, 121, 122, 123, on and on. Those are the leaf, where 1 and 2 is the stem. Now, let's go to this particular one here. We have 15 to 41, and we want to have our, our stem and leaf. Our stem is going to be the first numbers because, I mean, they are not as similar as the one we have here. So we have number 1, 2, 3, 4. And 1 and 5 here represent number 15. 1 and 6 represent number 16. 2 and 1 here represent number 21. 2 and 3, 23, 23. And that is what we call a stem and leaf. It's a very straightforward, arrangement. There's nothing really highfalutin about it. So you have your stem and then the leaf. So from this picture here, I can tell you that number 23 and number 26 are the ones appearing twice, just by looking at that stem and leaf plot. Okay. How do we make it? You arrange your data in order, you separate the data according to the first digits or digits, and you make a display by using the leading digit as the stem and the trailing digit as a leaf. This is another example here. We have 1, 2, 3, 4, 5 as our stem, and then on the side of the leaf, we can see the numbers there. Even looking at this particular stem and leaf, I can tell you that number 41 appears twice, number 35 appears twice. I mean, as straightforward as that. And then those in number 40 are about 5, unlike the others that are 3 and 4. So that's stem and leaf. And the same also applies here. From this particular stem and leaf, I can tell you the mode, the commonest number is number 17. It's appearing 3 times. I don't have to have them stretched out one by one, and then we have number 50 appearing twice. This 06 means it's just number 6. That's stem and leaf. Once you see it, it's straightforward, you can't miss it. It's just arranging the stem and then looking at the leaf and trying to read the meaning of what it means. And this is an example of a classwork. Steve got his friends to do a long jump and got these results, 2.3 down to 5.0. Construct the stem and leaf plot. So for our stem, let's have our stem here. We have 2 points here. There's 3 points. There's 4 points. There's 5 points. So we have 2.3. We have 5, we have 5, we have 7, we have 8. 3.2, 3.6, 3.6, 4.5, 5.0. That's all. As straightforward as that. There's really nothing beyond that. So all these axes are the leaves, but these are things that, what's it called? Softwares can plot for you, especially if you have plenty number. This is just very few. This is just like 10 or less. But if you have plenty number, that a software will be able to do that for you. But that's just a stem and leaf, So for a dot plot, it's a type of graphical display that can be used to show a data distribution. And the dot plot can be used for both quantitative and qualitative. This is categorical, that's qualitative, and this is quantitative, So a dot plot can be used for both types, interestingly. It takes the form of a bar graph or histogram, and that shows that it can be used for both. And there are 2 types, the Cleveland and Wilkinson. The Cleveland is similar to a bar graph. The Wilkinson is similar to a histogram. That's why they can be used for any type of variable. So look at it here. Look at the Cleveland. Here, the dots are arranged. They are stacked together, to give a bar kind of appearance. You can see it's like there are spaces in between them, So here, the number of books read, 0. Maybe if we count the number of dots, it might be the number of participants. So 4 people read notebooks. Maybe 6 people read 1, 3 read 2, only 1 person read 3, 2 people read 4, on and on like that. That is for a dot plot for a Cleveland type. Whereas on the Wilkinson, it looks more like, you know, the histogram. Here we have long jump. And from here, we can see that the ones with the longest distance is from United States, and the one with the shortest distance is from Indonesia. So it's just to trace it down to have an idea of the corresponding figure. They are all dots, you know, but one is for like histogram, the other one is for like a bar chart. This is another example, number of brothers and sisters. Those two people do not have brothers and sisters, you know, three people have one, 5 people have 2, 3 people have 3, 2 people have 4. As simple as that. And you can also see here, you know, another example of this one is the Wilkinson, you know, that's another example of dot plot. Now, a line chart, let me just go back. It looks to me that if you join a Wilkinson, you know, with a line, it makes it look like a line chart. So imagine this particular line chart without the lines connecting them. It makes it look more like a Wilkinson dot plot, you know, but it's just like to show our appearance, to describe the appearance of our data. So this is an example of a line chart. This is an example of a line chart here, combining 2 different variables, you know, A and B, to see if there's any kind of association or difference. This is another example of a line chart. You will see all manners of line charts, but they are just like describing our variables. And this is a time series plot. A time series plot has to do with timing, you know, something that is chronologic, and you are trying to like pick it, and it's like all these circles are the particular observation, and they are joined by a line. They are joined by a line. That's why it's a time series plot. And so in a nutshell, descriptive statistics, you can either organize your data, or we have just been discussing about organizing data. Let's quickly look at summarizing the data, where the issue of the central tendency comes in and variation. So we talk about summarizing data. And when we talk about summarizing data, you do it with interval or ratio data. That is, you do it with quantitative variables, ratio scale. Okay, and for the central tendency I mentioned earlier on, mean, median, mode, and for the variation, we have range, interquartile range, variance, and standard deviation. The mean is something we all know about. It's just adding up all the values and dividing by the total number of cases. The mean is the same thing as average. For all these numbers now, the mean is just adding 6 plus 4 plus 5 plus 4 plus 8 plus 3 divided by 6, and that gives you 5. That is the formula for a mean. We are all conversant with a mean. And this is an example like we've been working with for class A, 13 student, class B, 13 student. What is the mean weight? You add all the numbers, the weights together, divide by 13. It gives you 110.5. For class B, 110.23. All those ones are straightforward. Now, the mean is very important when you are doing inferential statistics. And the mean is not resistant to outliers. Some of us are coming across this terminology for the first time, and it's very important we grab it. An outlier is a person or thing situated far away or detached from the main body or system. An outlier can also be a person or thing different from all other members of a particular group or set. Okay, and I will explain what an outlier means. So the mean can be badly affected by outliers. Please, very important. When you have a data set that has an outlier, don't use your mean to describe the data set. That's what I'm trying to say. Outliers can make the mean a bad measure of central tendency or common experience. For example, let's assume all of us in this group, we are looking at our income, and then Dangote is part of this group. By the time we add Dangote and we calculate the mean income for all of us, it's going to give us a wrong impression. You know, if all of us were earning, like say in 1 million, let's say all of us are earning $1 million, you know, and then we add Dangote, who is earning like maybe like 4 billion. Maybe like $4 billion. By the time you find the mean of 1 million and 4 billion, you'll be having a wrong impression of our income. So whenever you have an outlier, do not use a mean to describe your data or to summarize your data. Very important. This is an example of, will I say, this is an example of like a Cleveland dot plot, if you look at it. Because here, talking about income, we have 2 people, you know, earning $15,000 per annum. We have about 7 people earning like 20, on and on like that. This is a good example of like a Cleveland dot plot. It doesn't have to be dots. Anything can be used. And then we have, if I want to do like what's it called? A normal curve, you can see that it has a very long right skew. Long right skew. In a situation like this, you don't want to use a mean, because if we were to calculate the mean of our income, it falls to something like 70. I have done the calculation here. If you calculate all the values of the monies here, you are going to get 2,100, and there are 30 families here. Divided by 30, it will give you $70,000, maybe per annum. And that is not a good, representation of this data. This is the bulk of the data, and this is not the mean income. And this is because only 3 people are earning more. These 3 people are more like outliers. They are beyond the normal range of what we are earning, and they have caused the value to be a bit different. So when you have a distribution like this, you do not use a mean to describe your population. It's going to give you an erroneous finding. So the mean is the best measure of central tendency. It uses all the data and is affected by extreme values. So when you have outliers, please don't use your mean as a measure of your central tendency. It is best for a normally distributed data, and the mean not usually equal to one of the original values. It's usually like an average, and it has good statistical properties. So in research, the means are usually presented along with standard deviation or standard errors, and we are going to talk about standard deviations as we continue. The median is the middle value when the variables values are ranked in order, either in ascending or descending order, and you look at the one that divides it into equal halves. When the data are listed in order, the median is the point at which 50% are above, 50% are below. Another name for median is the 50% percentile. So for example, in class A, there are 13 students. If we order them in ascending order from 89 to 140 for their weight, the middle number is 109, and that is the median. It's as simple as that. And this is because our number here is odd number. So let's assume maybe the first student is no more, and we now have 12 students. That is where we now have to look at the middle point, and we have the first 6 and then the second 6. We will now have to add the first, the last number on the first 6 and the first number on the second 6. We add them together, divide by 2, and that gives us our new median. As simple as that. There's no more calculation for median. The interesting thing with median is that it's unaffected by outliers. So no matter what the outlier is, it's the middle point that we're interested in. It doesn't factor in outliers. So it makes it a better measure of central tendency when you have outliers, describing a typical person, when you have, when the mean is skewed. If the recorded values for a variable form a symmetric distribution, the mean, the median, and the mode are actually on the same line if it is a very perfect distribution. In skewed data, the mean lies towards the area of the skew, like we saw, The mean lies towards the area of the skew when you have a skewed data. For example, you can see that this is the mean. It lies towards the area of the skew, but the median is the middle number. It's not much affected, but it's still closer to the area of the skew. The properties of the median, it does not use all the data available. It's insensitive to outliers. It's a good descriptive measure, but it has poor statistical properties. It is the measure of choice, like I've been emphasizing, when you have skewed data. Let me give us a practical example. You have maybe a class of 10 students, and you give them an exam over 100, and that's over 100. Maybe this one has 21, this one has 24, this one has 18, this one has 17, this one has 31, this one has 11, this one has 20, this one has 23, this one has maybe, let me say 19, and this one has 95. That's 10 students with 10 scores. If you are going to describe this particular stuff, a mean will be very wrong. Because by the time you add all these numbers plus 95 and you divide by 10, it will be giving you a number possibly close to like 40 or 45, thereabout. And that will give us an erroneous view of the performance of the student. So when you have a distribution like this, please don't use a mean. Rather, you use a median. And you can calculate the median by arranging them in ascending order and look for the middle value. That's all I'm trying to say, that for a skewed data, because this one is obviously an outlier. Most of your students are between, say, 11 and 32 or thereabout. 95 is a genius, is not an ordinary student. So an outlier, it will affect you using, you'll be affected using mean to describe that. Mode is the commonest data point and is the straightforward stuff. It doesn't have so much problem, you know. It's just the number that applies more commonly among the data points. You might have a data set that has no mode. For example, this one, there's no mode. And you can have another data set with a mode, like here, number 3 appears 3 times. That's the mode. And you can even have a distribution that has 2 modes. We call them bimodal. Like this data set, number 2 and number 5 appears twice. That's bimodal. It gives you the most likely experience rather than the typical, this is median, or central, that is mean. In symmetrical distributions, the mean, the median, and the mode are the same. That's if its distribution is symmetrical. But if it is skewed, the mode is the further ones away from the skew side. You know, it's usually common, it's away from the skew side. So you can see here, that's the mode. Is the one furthest away from the skew side, followed by the mean, and the median is always closer to the area of skew. So like I said, in a normal distribution, the mean is the same thing as the mode and is the same as the median. So that is for summarizing our central tendency. So for the measures of dispersion, let's talk about range. Range is very straightforward. It's just the difference between the highest number in the data and the lowest number in the data. So for class A, the highest weight is 140, the lowest weight is 89. The range is just that, 140 minus 89, 51. For class B, the highest weight is 162, the lowest is 80. The range is just that, as simple as that. That's the range. Interquartile range is when you divide your data into quartiles, that is into 4 equal parts. A quartile is the value that marks one of the divisions and breaks the series of values into 4 equal parts. The median is a quartile that divides the cases into half. That is a Q2. The 25th percentile is a quartile that divides the first quarter from the latter third quarter. And the 75th percentile is a quartile that divides the first 3 quarters from the last 1 quarter. That is the interquartile range. So this is an example that I want to quickly do, hoping we have enough time to tidy it up before we continue. So there are 12 patients here, and they were examined to see the number of push-ups they can do after a plate of food. You know, these are the number of push-ups they did after a plate of food. And we are told to find the 3 quartiles and the semi-interquartile range. So the idea is to actually arrange them according to ascending order. So let me start by saying I have 8, I have another 8. So let me strike these ones out. Then I have number 9. I think I have number 10. I have 11, 1, 11. Then I have number 12. I think I have 14. 14, 14, 14. That's 1, 2, 3. Oh, 14 is 4. There are 4, 14. Then I have 16 and 19. 16 and 19. Awesome. So that's 12 of them. So the first thing to do is to find the median, which is the Q2. And like you see, there are 12. So I can count from number 1 to 6. 1, 2, 3, 4, 5, 6. This is 6, and this is the other 6. So my median is just going to be here. That is 12 plus 14 divided by 2. That is 26. That's 13. So my Q2 is 13. Now that I have this one in this group, this one in the group, for my Q1 and my Q3, it's just the median again. My Q1 is not the median of this particular group. My Q3 is the median of that particular group. So my median here is going to be 9 plus 10, that's 19. That's am I right? 9 plus, yeah. So that's my Q1. My Q1 is 9.5, and here is 14, 14. So if I find the Q3 here, that's 14 plus 14, 28 over 2. That's so my Q3 is 14, as simple as that. That is Q1, Q2, Q3. So those are the three quartiles. The next question says the semi-interquartile range. The first thing to find out is the interquartile range, which is actually Q3 minus Q1. That's interquartile range. That's 14 minus 9.5. I think that should be giving you 4.5, if I'm not mistaken. 14 minus 9.5, I think that's 4.5. Yeah. So Q3, 14 minus 9.5, that's 4.5. But look, the question actually said semi-interquartile range. So I now have to divide this by 2 to have the semi part. That was 2.25. That's the answer. So it's a very straightforward stuff. There's no big deal. But this one is just like a classwork in case you are doing a classwork. If the numbers are very massive, the softwares can do that for us. So look at this particular example here. It says the interquartile range is the distance or range between the 25 percentile, which is Q1, and the 75 percentile, which is the Q3. So below, what is the interquartile range? We have our Q3 here as 15. We have our Q1 here as 4. So interquartile range is 15 minus 4, which is 11. Our interquartile range is just 11. It's a very straightforward stuff. And that is our range, interquartile range. Great. Then we talk about variance, which is a measure of spread of our values, a measure of dispersion. The larger the variance, the flatter our distribution. The smaller the variance, the more closer together the scores are. So this one is a platychotic. Remember we discussed that earlier on, platychotic distribution. This one is leptochotic. And it's just a sign that our variance is closer together. There's no much difference from the middle. Consider these numbers. If you are to add all these numbers and find their mean, you will get 5 for all of them. This one is a constant. So there's no variance. This one now, you will have a larger variance because we have a number as far as 1, another one as far as 9. This one too, you will have a variance, but it might be close. This one too is going to be close. But that's how it works. The constants have no variance. They have no standard deviation. The other numbers are a bit like dispersed, so you have more variance. So look at that example we've been working with, our class example for class A. Remember, we have 11 and 13 students, and our mean was 110.554. So the question is, what's the deviation of our mean, our finding, our observation from the mean? So we want to look at how far away this is from the mean, how far away this is from the mean, and even to check for all of them. That is the deviation we are talking about. So for 102, the deviation is minus 8.54. For 115, the deviation is 4.46. And if we are to do it for all the numbers, there are those that will be minus, there are those that will be positive. And if we add all of them together, we are going to get 0. Why? Because the positive will knock off the negative. The positive will knock off the negative. And we need to eliminate the negative signs in our dispersion, in our variance. So what do? We square all those numbers, both the positive and the negative, and then we add them together. So back to that example, 102 minus the mean gives us minus 8.54. If you square it, we have that. For the one that is positive, if we square it, we have that. And we will do that for all the numbers. That's 13 observations. We add all of them together, and we have what we call the sum of squares. Sum of squares. Please keep that handy. I think in our third lecture, we'll be talking about sum of squares. So if we have all that added together, the one that are negative and positive, we end up with 2,825.39. That is our variance. That is our variance. Now, for us to now have the average variance is for us to divide by the number of observations. If we are working with a population, you just divide by the total number of population. But if you are working with a sample, which is most of the things that we work with, you divide by n minus 1. That's the sample minus 1. So our variance, let me just go to the next slide. Our variance is now going to be 2,825.39 divided by 12. Our 12 is 13 minus 1, if you recall. That's 13 minus 1. And we are having 235.45. The truth is that that does not really give us any value, because the value of variance are squared, and it makes it hard to interpret. It makes it hard to interpret. So what do? We convert our variance to something that is more meaningful that we call standard deviation. So in a nutshell, standard deviation is just the square root of a variance. So if you can calculate a variance, automatically you should be able to calculate a standard deviation. So the square root of the variance reveals the average deviation of the observations from the mean, as simple as that. And the standard deviation is no longer squared, since it's the square root of the variance. That is the square root of the S squared, which is our standard deviation. And once you have that standard deviation from that particular one, it's giving us 15.34. That's the average person's deviation from the mean. That's the mean weight. And I'm going to explain what that means in the subsequent slides. So we have deviation squared, the sum of squared, the variance, and the standard deviation. That's what we've done in the previous slides. Now let's talk about that standard deviation. The larger the standard deviation, it just shows that the more the variance. The larger the standard deviation, the more the variance. The smaller the standard deviation, it shows that the smaller the variance from the mean, that's from the center. When your standard deviation is 0, all the values are the same. That means a constant. So we have a mean here of 25 and a standard deviation of 3. We have a mean here of 25, a standard deviation of 6. You can see the way the distribution looks like. And if our mean is to be rescaled from this 25 to 250, our standard deviation will also be scaled in the same multiple. It will become 30. And this one will become 60 also. It's just a very straightforward stuff. It's a function of, the mean. Like the mean, the standard deviation will be inflated by an outlier also. Like I said, here our standard deviation is going to be 0. This one is going to be a bit high, less, because there's a lot of variance here from the center. Now, look at a normal distribution here. When we have a normal distribution, by default, 68% of our observations fall between one standard deviation of our mean. 95 falls between 2 standard deviations of the mean, and a 9 will fall between 3 standard deviations. And I'm going to explain what this means very soon. You understand? That is if we have a normal distribution. So if a distribution of data is approximately bell-shaped or normal, 95% of the data should fall within 2 standard deviations. By the way, when we calculate our standard deviation, it is 1 standard deviation that we have calculated. When we calculate it like we've done in the previous slide, it's just 1 standard deviation, okay? So like I said, 68 between 1 standard deviation, 95 within 2 standard deviation, 99.7 within 3 standard deviation. So look at this class example. Suppose that the reaction time of a particular drug, a pain reliever, has a normal distribution of 10 minutes. That's the mean. We have found the mean of 10 minutes and a standard deviation of 2 minutes. What does that mean? What does that mean? Yes, Dr. Lawa.
Yes, sir. We have 20 minutes, 20 more minutes.
I intend to finish in the next less than 10 minutes so that I can still take some questions.
Okay.
But yeah,
Okay,
I don't know
thank you very much.
I will try and tidy up very soon. Thank you.
Thank
so
you very much.
suppose the reaction time of a particular drug has a normal distribution, with a mean of 10 minutes. So this is our mean, and then we have plus or minus 2 minutes. What does that mean? What does that mean? Recall that particular slide where I said 68%, are within 1 standard deviation, 95 within 2 deviations, 99 within 3 deviations. It means that 68% of patients that take that medication should expect to have, maybe relief from their pain between 8 and 12 minutes. How did we get 8 and 12 minutes? Remember, our mean is 10 minutes, and standard deviation is either plus or minus. So 10 minus 2 will give you 8, 10 plus 2 will give you 12. So 68% should be able to have reaction of pain relief between 8 and 12 minutes. 95%, now I'm talking about standard deviation, should be able to have some pain relief between 6 and 14 minutes. That's 2 standard deviation. Remember, our standard deviation is 2. So 2 is going to be 4. That is 10 minus 4, 10 plus 4. That is 6 and 14. And nearly all of us taking the medication should have a reaction of pain relief between 4 minutes and 16 minutes. That's 3 standard deviations. That's how you interpret standard deviations, okay? Now look at these two classes. We have class A with a mean of 80, standard deviation of 5. Class B with a mean of 80, standard deviation of 15.8. That should speak some things to you. They both have the same mean, but their standard deviation differs. This particular one here shows that most of the scores are close together, whereas the one with a higher standard deviation shows that there's a kind of range, a higher range. We have 60, we have 100, 100. That's how you understand and interpret your mean plus standard deviation. When the standard deviation is small, it shows that the observations are close together. When the standard deviation is high, it shows that there is a higher dispersion, you know. And if you have a mean plus or minus standard deviation and the standard deviation is greater than your mean value, that means you have an outlier. And that's a good indication that you shouldn't use your mean to summarize your data. I'll go over that again. If you have a mean plus or minus standard deviation and the standard deviation value is greater than your mean value, that means you have an outlier and you shouldn't be using that to explain your data. So we have discussed all that: mean, median, mode, range, interquartile range, variance, standard deviation. The last thing I want to talk about is box plots. And it's a graphical way to portray almost all your descriptive statistics. You know, it can show you the upper and lower quartiles, it can show you the mean, the median, the range, and it can show you the outliers. That is just in one plot. That's how it looks. It has this beautiful appearance. You know, that's the box plot. We also call it a whisker plot, okay? And that's another appearance of a box plot. That's another appearance of a box plot, different designs, different shapes, different coloration. But this is the interpretation. When you have a box plot and you have something outside, that's an outlier. The whiskers, the upper one is the maximum, the lower one is the minimum. That dark line that you see is the median or the 50th percentile or Q2. This part here, upper quartile, is the Q3, and this part here, that's the Q1. That is what you see in a box plot when you have it like a graph. It gives you a lot of information in just one chart, and that makes it a bit, it summarizes a lot of data, you know, at the same time. So box plots have lower quartile to upper quartile with median marked. They portray a 5-number summary of the data: minimum, the lower quartile, median, upper quartile, and maximum. And they can also show you, you know, an outlier. You can calculate an outlier using the formula, you know, the lower quartile minus 1.5 interquartile range for the lower outlier. An outlier above the upper quartile is usually upper quartile plus 1.5 interquartile range. By now, you know what an interquartile range is, you know, and then you can calculate that. So this is just an example of an outlier. We've read that, you know. So now you are qualified to use descriptive statistics. I don't know if there's any question. I was hoping that I might be able to show us maybe in the next 5 minutes some things from SPSS on how we can do some of this analysis. I have a sample data with the following variables. We have age, which is continuous. We have the gender. For this one, I'm using binary. We have what we call a basic metabolic index, is a continuous variable. The lipid level, continuous variable. Presence or absence of stroke, binary. Hypertension, presence or absence of hypertension, binary. Educational level is ordinal. Income per day is continuous. I don't know if I still have time to do that in the next 5 minutes.
Yes, sir, we have 14 minutes more and some questions too. Okay. So if you can take 5 minutes, then please indulge of the audience to stay 5 more minutes extra.
Okay, let me just quickly share the slide so that let me quickly 1 minute, please. Can you see my slide?
It's Yeah, sharing. Okay.
Beautiful. Okay, so this is just a sample SPSS data page. And like I said, it's just hypothetical, not really the truth. I have here some variables: age, gender, BMI, the lipid, presence or absence of stroke, number of people followed. I have here hypertension, educational level, income, and BMI too, just hypothetical. And it's for, 1 minute, it's for like 180, observations. That's my sample size, for example. So the first thing I want to do is to, now by virtue of what we have discussed, we have age as a continuous variable. Gender here, I'm using male and female only. That's a binary variable and that's a nominal variable. The basic metabolic index here is the continuous variable, the lipid is continuous variable, and on like that, just for us to understand, If I go to analyze here, I can come to descriptive statistics here, and I can come to frequency here. And okay, I have some example of variables already put here. Let me just I want to just show us how I got here so the variables are already on the left side. I was the one that chose them, for analysis. So I came to gender here. I moved it to my variable column. I came to maybe presence and absence of stroke. I came to hypertension. I moved them there. And you will notice that the ones I'm moving to the variable columns are the categorical variables, because all I'm trying to do now is just to generate a table for it. Okay, maybe educational level also here. I can go to statistics here and okay, because as you can see, it's not highlighting anything because they are categorical variable. So I just cancel and let me just place okay. I will have to share that particular output. I have to share the particular output page and we'll continue from the output page. 1 minute, please. Yeah, Adele. All right. So I will continue with this output page. I won't go back to the slides again. But as you can see from the output page here, I have my sex. Where's my cursor? I have the sex here. It shows the male and female, as you can see there, and their percentages. Those who have stroke, you can see the male and female for no and yes. And those who had hypertension also, you can see the frequency there. Educational level, you can see there. Those that have primary, non-secondary, and tertiary. And since all those variables are categorical variables, you can see that it's coming out with a bar chart. I've highlighted that as part of what I wanted. We have the bar chart for gender. We have the bar chart for those who had stroke, those who had hypertension. From the bar chart, you can see that hypertension, there were more people with no. For stroke, there were more people with no also. And in educational level, you can see that we have nearly primary, secondary, and tertiary having maybe fairly the same amount of people, for, what's it called? For frequency. I go back to maybe my analyze and descriptive statistics. Sorry, analyze, and then I pick descriptive statistics. And there's this pop-up that is disturbing me from those who are in the waiting room. It's covering my work. Descriptive statistics, descriptives. Here I have 4 variables: the age, the BMI, the lipids, the income per day. I have put them as the variables I want to check for descriptives. And here for my options, I have already highlighted all those variables I'm interested in. I'm interested in their mean, the standard deviation, the minimum value, the maximum value for the range, the variance, the range. I want to see the kurtosis also, like we mentioned, and the skewness. I told us that it can be done easily by the software. And then maybe I continue here, and then I press OK. And I expect it to Let me just scroll down. You can see from this table here that we have all those information given just at the click of a button. For the baseline age, the total number is 180. We have the minimum age as 31, the range as 31, which is just the subtraction of 32 from 63. The baseline also, the range is 18.9. The lipid level, the range is 391. The income per day in Naira is 350. It's just subtracting 10 from 360. On and on like that. And you have the mean, you have the standard deviation, you have the variance, you have the skewness, and you have the kurtosis. I think I'll just do only one more analysis to allow us time to hear one or two questions. I'm going to do an example of, what's that called? Let me do a box plot. Yeah. So I go to graphs, to legacy dialogues, and then to box plot. And then a simple box plot. And I want to check the variable baseline age, and I want to compare it. Okay, no, let me compare it with educational level. Let me compare with educational level for you to see how it comes out, and I click OK. And there you are. Beautiful. So we have the summary of those who did not go to education, who don't have any educational level. That's 0, primary, secondary, and tertiary. That's a box plot. And as it is now, there's not much time. We can recolor them, to differentiate each category from each one of them. We can do a bit of formatting just to make it look more appealing. But that's a box plot, and that's how it looks. And remember, we said that the upper part there, that's the maximum. The lower part here is the minimum. This is the Q1, that is the Q3, and the middle part is the Q2. That is the median, or the 50% percentile. I will want to stop here. I have like 5 more minutes so that we can take questions if there are, and any comments. And to thank you for your attention all through. Dr. Lawal, over to you. Thank you so much.
Thank you, and thank you very much. As you can see on the chat box, a lot of appreciation to show how much people appreciated what you've done for us. There are a lot of questions that have been asked. I will just pick some and try to answer others on the chat box, on the WhatsApp page later
awesome.
on.
Yeah.
Okay, so let me just pick some of them that just a minute. Somebody asks what factors can influence a constant value?
Come again.
What factors can influence a constant value? I don't really get the question.
No, nothing will influence them. It's constant. So nothing is influencing it. There's nothing you can do about it. It's just constant.
Okay.
I doubt if any factor will influence it, yeah.
Yeah. There is a question about differentiating between moderating and mediating variable.
Oh, okay. Moderating and mediating variable actually are synonyms. Okay. They mean the same thing, yes.
Okay. Somebody wants to know whether there is a difference when to use cumulative and relative frequency.
Okay, so that's a choice about your own analysis. It depends on your research question. So if your research question wants to know the total number of people at a particular frequency level that have a particular function, that is when you use cumulative. And I gave an example during the course of the lecture, like I was talking about the number of books read, that somebody read 1, somebody read 2, they were in like 1, 2, 3, 4. So you might want to have a cumulative at the group level of 4 to know those who have even read from 1, 2, 3, because for you to read 4, you must have read 1, 2, or 3. So you want to have like the total sum of all the people that have gone through 1, 2, and 3 in 4. That is where you have a cumulative figure. So it depends on your research question. If you want to know like how many have been beneath a particular frequency group, a particular observation group. So it's not as if it is sacrosanct that you must use it. It's your question that will determine the choice of using it or not using it.
Okay, thank you very much, sir. Someone is asking the maximum number of variables, categorical variables that will determine the use of pie chart?
The maximum number of variables that will determine the use of pie chart, categorical variables. Yeah. Okay, so I don't think it's, I've not come across anything like that. Yeah. But what I have found out is if your variables are too much, your pie chart will have too many tiny segments and it will be useless. You get the point. So if you have too many variables, it will be difficult to read out from your pie chart. So you might need to use another method to describe your data. Good question. Good question.
Yeah, rightly said, sir. I think I've come across a book that talks about more than 7. It becomes standard, but like you said, it's not cast in stone. Yeah, the next one talked about when you're talking about not using mean if there are outliers. The person is asking about cleaning the data.
What about what?
Can you do that? If you remove the outlier by way of data cleaning.
Yeah, so if you remove the outlier, you can use your mean. Sometimes outliers are mistakes in data entry. You want to type 11, you press the keyboard twice, 3 times, 111, you have 111. So once you clean your data and you don't have outliers, then you can use your mean. It's just to safeguard us against erroneous presentation or reporting. So once you don't have outliers, please go on and use your mean.
All right, some of these have been answered. Okay, somebody is appreciating that this should be paid for. Just a means of appreciating you. Thank you once again, sir. Somebody asks, what other things can you use if mean cannot be used when there are outliers? I think you've addressed that already.
Yes, mean and median and mode.
Yeah. Someone's asking, is there a difference between multivariate and multivariable when it comes to analysis?
Beautiful. There is a difference. I wouldn't want us to talk about that now since we are going to
we'll come
analysis.
To it later.
We'll come to it later, yes.
Yeah. Thank you. Can a line diagram be used for continuous and discontinuous variable?
Anything line has to be for a continuous variable.
Continuous variable. Thank you.
Yes, yes.
Yeah. The next one is when standard deviation is greater than the mean, you said we should not use mean. What measure of variation should we use, sir? I think you answered that already.
Yes.
Okay. Yeah. Let me just pick those that put on the chat on the WhatsApp group. I think we've addressed most of the questions. Let me check the chat box. Oh, can data cleaning lead to bias?
Can what?
Data cleaning lead to bias?
It depends on how you clean your data. You know, there are some data that you have outliers and the outliers are actually true. So you don't clean them off. Rather than now using a measure that will bring in bias, like a mean, you use other measures to summarize the data. So if you are in there deliberately removing some figures from your data, that's fabrication and falsification, and that's bias. So it can lead to bias, but we don't advise you do bias for your data. You know, we want you to report exactly what we have found, you know, so that we can have the true picture of your findings.
Thank you, sir. Someone is asking for the difference between standard error of mean and standard deviation. When
we
can wait mean of to the next.
We can wait for that for the next when we are discussing t-test, because I want to go like a step at a time so that I don't bring in some concept that might scatter what we are trying to build.
Yeah, thank you. Many of the other questions will be addressed in subsequent lectures. That's why I skip them. Yeah, thank you very much, sir. We really appreciate what you've done.
Thank you, Doctor.
Like I always say, I've attended many trainings on research and manuscript writing and data analysis, but yours is always a unique one in the sense that you break it down to basics, and every time I learn something new. Thank you very much, sir.
Thank you for the opportunity.
I just want to pass some messages across to the participants so that it makes the work easier for us doing the administrative work in the class. Please, when you are joining the class subsequently, ensure that your name is full name is used for your page. Don't use DOS or DOE or any abbreviation. This is to avoid hackers from hacking the class. We know all that can happen with hackers. So please, let's use our full names. Subsequently, I allowed some people in later in the course of the class, but subsequent classes I'll have to remove. And once you are removed, you can't rejoin the class. I put many people on waiting list because they use their device, the Samsung and Nokia. For subsequent classes, we'll have to remove you, and that will mean you won't be able to join the class. As usual, our classes are usually from, so we start 8 and we end by 10, so that you can do other activities of your day. So please try and join early. Normally, usually we open the class 10 minutes, 10, 15 minutes before the start, so you can join early and we'll start early. Those who are asking for recordings, the link, the YouTube link has been shared, and you can access the recording directly on the YouTube page right away from now on. The slides have been shared in the WhatsApp group already, so you can start reading it and to read ahead of the class so I can ask questions where there needs clarification. We'll continue the conversation on the chat box. Everybody, I'm sure everybody have a nice time in this lecture, and we'll continue the conversation. Like I said, thank you for being with us. Thank you. You have a nice day.